College professor here. We're going to go over the central limit theorem today. It's a continuation from the empirical rule normal distribution curve. So the central limit theorem says that if you take a lot of random samples from any population and calculate the average of each sample, the distribution of those averages will look like a normal distribution bell-shaped curve. So again, the more samples going to look like a bell-shaped curve and normal distribution. We get closer to normal as your sample size gets bigger. So when the sample gets over 30, you're going to get more of that bell-shaped curve. You'll have a mean equal to the population mean. So again, we talk about that mean. You'll get closer. When you get more samples, you'll get a mean that's equal to that. You'll have smaller standard deviations than the population standard error. So we know that from our past. Why does this matter? It's super important because it allows us to use the normal distribution techniques even when the population isn't normal. We can make predictions and run hypothesis tests and averages. And we can estimate those confidence intervals. So again, we can use the normal distribution technique. Really helpful to us, the curve. It goes even further and tells us that the mean and the standard deviation. Some of the calculations that we can use, we're looking at the parameter, population distribution. We have our mean and our standard deviation. The notation for the sample, x bar, small s, and then the sampling distribution of the x's. Again, we have our formulas here with the means and the standard deviation. This formula will come in handy, the new standardization formula, or standardization formula. Now, the law of numbers, it proves that the expected value of the sample distribution of the sample mean is the population mean. So again, when we take so many samples, the sample mean becomes a population mean. So when we have a sample size, a smaller one of 10, we're kind of in the normal distribution curve, but when you get more samples, it's more tighter. And you can see that here. At a very large sample size, the standard deviation of the sampling distribution becomes very small, and at infinity, it collapses on top of the population mean. So again, that just means the sample mean and the population mean will be the same when you have large sample size. What we can also see too is the standard deviations of the sampling distributions decrease because the sample size is the denominator of the standard deviations of the sample distribution. So again, the larger the sample size, we have less at 50 deviations from the mean than if we have a sample size of 30 or 10, much further away from the mean. The standard deviation of the sampling distribution for proportions. We can see here what parameter are we measuring, mean, standard deviation. We have our population distribution, sample, and the sampling distribution of our samples. So again, good formulas to keep in our mind. Now, if you have a finite population, there is this correction factor that we use. As the population becomes smaller and we sample a larger number of the observations, the sample observations are not independent of each other. To correct for this, we use the finite correction factor. It can be seen there and there. And it can be used to adjust the variance of the sampling distribution. It is appropriate when more than 5% of the population is being sampled. So if you sample more than 5% of the total population, it comes into play. So again, good formulas to have. Now, the assignment questions for this week is really going to focus on understanding the required sample size. So I've given you this formula here that's going to come in extremely handy as you work on those calculations. Extremely handy. So let's take a look at that. We're going to start out and go with the first problem. So again, this formula is going to really help us out. A company wants to estimate the product defect rate with a standard deviation of 0.7. So standard deviation, 0.7. An allowable error of 0.59. And a confidence interval of 98%. So we need to get the z-score to figure. We need the z-score from that confidence interval. And remember the area under the curve. So we want a 98% confidence interval. So we need to get the z-score. So to start us off, we have some of the items in this formula. N is the sample size. Z, we don't know what the z-score is yet, but we do know what the standard deviation is and the error that we're looking for, allowable. But we need to get the z-score. So what is the z-score? Now here's an excerpt from the z table. And we're really going to look up reverse of the way that we looked at it before. Now we know that the z-score looks at one side of the everything to the left. So we know that it's the one side of the equation. So the trick with this is we take 98 divided by 2. Or 0.98, 98%, 0.98 divided by 2. And we get 49.49. Because we're looking at both sides. So 0.49. Now, when we look at this, the table, I'm just filling this out. Now, we're looking for 0.49. 0.49 is basically right here. It's basically 0.3. Pretty close. So now we grab the 2.33. Pretty close to that. And that is our z. So you go 2.33 times 0.7 divided by 0.59 squared. So get out our calculator. There's times 2.33 times 0.7 equals divided by 0.59. 2.76440678 squared. Gonna square that, and we get 7.64. Now they say round up because you can't have a partial sample. So n equals, we round that up to 8. So the sample that we need, the sample size is 8. So we need a sample size of 8 to make sure all the conditions apply. So sample size of 8. Let's continue on. So you're going to get a problem like that. Now here's another one. A company wants to estimate app usage time with a standard deviation of 2.3 standard deviation, error of 0.69, and a confidence level of 90. Again, we have our normal distribution. So 0.9 divided by 2, 0.45. Now, this one here you can see in this example, it's different than the other one because 0.49 is so close to that. So that's pretty obvious. We use the 0.03. But when it's 0.45, it's kind of in the middle here. Exactly in the middle, actually. 0.45. It's pretty much in the middle. It's more than 0.4495 and less than 0.4505. It's right in the middle. So in this case, we have, going to just fill this out because the table was cut. So it's in between 0.04 and 0.05. So we can say it's 1.645 because it's right in the middle of 0.04 and 0.05. So it looks like it should be 0.045. So again, add that to the 0.6 and we get add that to the 1.6 and we get 1.645. That's our z-score. Again, we're just doing the reverse and using the z-table reverse of what we did last class. Now we have everything we need for the formula. Let's go back to the formula. Just hide that. So n equals z is 1.645 times standard deviation 2.3 all over the error of 0.69 squared. Use your calculator, do the 1.645 times 2.3 divided by 0.69 and we get 548, repeating, squared, square that, and we get 30.0669. Now again, it says round up, so n equals, round that up, even though it's 0.06, we round it up to 31. So the sample size is 31. Okay, so that's the logic behind the questions that you're going to be looking at for this week's lab. And again, hopefully it makes sense to you now. Thank you for watching. College Professor out.